Imagine this. Only 600 million years after the Big Bang, a time when hardly any stars should exist, 6 huge, fully developed galaxies suddenly appear, massive, complex, and according to everything we know, impossible. These objects break every cosmological rule. If even one of them is real, something fundamental is wrong. Not in our models, not in our timeline, maybe not even in our understanding of reality. In the young universe, there was neither enough time nor enough matter to build such giants. Erica Nelson put it plainly: if just one of these galaxies is real, we have to rewrite our cosmological understanding. And that is exactly why this discovery is so unsettling. If these cosmic journeys fascinate you every night, don't forget to subscribe to our channel and like the video, because you will find more on this channel every night. Ready? Then let's begin. Part 1. Universe Age Crisis and James Webb Discoveries. James Webb Telescope's shocking discovery. Picture this. You're looking at photographs from the universe's childhood. Snapshots taken just 600 million years after the Big Bang itself. What you see shouldn't exist, not according to everything we thought we knew about cosmic evolution. Yet there they are, 6 massive galaxies staring back at us from the depths of space and time, challenging our most fundamental assumptions about reality itself. In 2023, the James Webb Space Telescope delivered findings that sent shockwaves through the scientific community. Published in one of the world's most prestigious journals, Nature, the research revealed 6 celestial objects that simply defy explanation. These aren't small, primitive galaxies struggling to form in the early universe. We're talking about massive, fully developed cosmic structures that appeared impossibly early in cosmic history. Here's where it gets mind-bending. According to our current models of how galaxies form and evolve, these giants should be at least 10 times smaller. Some calculations suggest they should be 50 times less massive than what we're actually observing. Think about that for a moment. Imagine finding a fully grown oak tree in soil that's only been around for a few weeks. That's the level of impossibility we're dealing with here. The problem isn't just that these galaxies are big. It's that they're big when they shouldn't have had the raw materials to become big. In the infant universe, 600 million years after everything began, there simply wasn't enough ordinary matter available. We're talking about the stuff that makes up stars, planets, and yes, even you and me. The mathematical models tell us there wasn't enough time for gas clouds to collapse, for stars to ignite, and for billions upon billions of stellar furnaces to congregate into these galactic behemoths. One of the study's lead authors, Erica Nelson, put it bluntly: if even one of these galaxies is real, it will push against the limits of our understanding of cosmology. Not bend those limits, not stretch them, push against them. That scientists speak, for we might need to go back to the drawing board on some pretty fundamental stuff. What makes this discovery particularly unsettling is its implications. We're not dealing with a minor footnote in astronomical catalogues. This isn't about discovering a new type of star or finding an unusual planetary system. We're potentially looking at evidence that our entire timeline of cosmic history might be wrong. The universe age debate. For decades, we've operated under a cosmic consensus. The universe is roughly 13.8 billion years old. This number isn't just pulled out of thin air. It's based on careful measurements of cosmic microwave background radiation, observations of distant supernova, calculations involving the Hubble constant, and a whole constellation of interconnected data points. Scientists have built entire careers on this foundation, but those 6 impossible galaxies, They're whispering something different, something radical. New theoretical work suggests that if we take these observations seriously, we might need to nearly double our estimate of the universe's age. We're talking about a universe that could be 26.7 billion years old. Let that sink in for a moment. We're not talking about adjusting our calculations by a few 100 million years here or there. We're talking about adding almost 13 billion years to the cosmic clock. How could we have been so wrong? It's a fair question, and it deserves an honest answer. The truth is, we might not have been wrong at all in terms of what we measured. We might have been wrong about what those measurements were telling us. Enter a concept that sounds like it belongs in science fiction: dark time. Now, before your eyes glaze over, let's break this down. We already know about dark energy, that mysterious force causing the universe to expand at an accelerating rate. We know about dark matter, the invisible substance that provides the gravitational scaffolding for galaxies. Dark time is being proposed as another piece of this cosmic puzzle. Something that could have sped up the development of cosmic structures in the early universe. Think of it this way. Imagine you're watching a video of a flower blooming. Normally, it takes days, but if someone's messed with the playback speed in certain sections, that flower might appear to bloom in hours. Dark time could be something similar for the early universe, a cosmic fast-forward button that allowed structures to develop much more quickly than we thought possible. But here's the kicker. This isn't just about adding a new concept to our cosmological toolbox. If the universe really is almost twice as old as we thought, it fundamentally changes our understanding of how everything evolved. The timeline for the first stars, the first galaxies, the heavy elements that eventually made planets and life possible, all of it needs to be reconsidered. The cosmology crisis and its impacts. Let's be brutally honest about what we're facing here. This isn't just an academic puzzle for scientists to solve in their ivory towers. We're potentially looking at a crisis for our theoretical understanding of space itself. The word crisis might sound dramatic, but in science, crises can be revolutionary moments. They're the points where old paradigms crumble and new ones emerge. Think about when Einstein's relativity overtook Newton's mechanics, or when quantum mechanics revealed the strange behavior of subatomic particles. Those were crises too, and they led to profound advances in human knowledge. Right now, with these James Webb observations, we're at a similar crossroads. The instruments are working perfectly. The observations have been checked and double-checked. Multiple teams have analyzed the data. The galaxies are real. They're out there, impossibly massive and impossibly old. So, if the observations are solid, then our theories must have gaps. Big ones. One possibility is that we've underestimated how efficiently early galaxies could form stars. Maybe the first generation of stars was more massive than we thought, burning brighter and faster, seeding the cosmos with heavy elements more quickly than our models predict. But even pushing these assumptions to their limits, scientists struggle to explain what James Webb is showing us. Another possibility involves dark matter playing a more active role in the early universe than we've assumed. Perhaps the invisible cosmic scaffolding that holds galaxies together was more concentrated or behaved differently in the universe's infancy. This could have created gravitational wells deep enough to pull ordinary matter together much faster than we thought possible. Or maybe, and this is where things get really interesting, our understanding of gravity itself needs refinement. Einstein's general relativity has passed every test we've thrown at it for over a century, but at the extreme conditions of the early universe, perhaps there are subtleties we haven't accounted for. Modified theories of gravity have been proposed before, usually to explain other cosmic mysteries. Could the solution lie in that direction? The fascinating part about this crisis is that it's not happening in isolation. Other recent observations have raised their own questions. The Hubble tension, for example, refers to conflicting measurements of how fast the universe is expanding. Different methods give different answers, and the discrepancy has only grown more pronounced as our instruments have improved. Could these puzzles be related? Are we missing something fundamental about how the cosmos operates? What makes this particularly challenging for scientists is the humbling realization that we might need to question assumptions we've held for decades. The scientific method is designed for this: make observations, form theories, test predictions, revise as needed. But there's something deeply unsettling about realizing that the cosmic timeline you've built your career on might be wrong by a factor of 2. Yet this is also what makes science exciting. We're not dealing with dogma here. We're dealing with the best explanations we have based on the evidence available. And when new evidence arrives that doesn't fit, we don't ignore it or explain it away. We roll up our sleeves and get to work. The confirmation process is crucial. Before we tear up the textbooks, scientists need to be absolutely certain these observations hold up. Are we really seeing what we think we're seeing? Could there be some exotic dust configuration in the early universe that's making these galaxies appear more massive than they are? Could gravitational lensing be playing tricks on us, magnifying distant objects in unexpected ways? These questions need answers. Multiple independent observations are required. Different telescopes using different methods need to examine the same regions of space. The James Webb results need to be cross-checked against observations from ground-based telescopes, from the Hubble Space Telescope, and from future instruments not yet launched. But if these observations hold up under scrutiny, we're looking at a paradigm shift. The kind that only comes along once or twice in a generation. The kind that redefines what we think we know about the universe's history, structure, and evolution. For those of you watching who aren't professional astronomers, you might wonder why any of this matters. Why should you care if the universe is 13.8 billion years old? Or 26.7 billion years old? What difference does it make to your daily life? Fair questions, but here's the thing. Understanding the universe's history is understanding our own origins. Every atom in your body was forged in the heart of a star. The iron in your blood, the calcium in your bones, the oxygen you're breathing right now, all of it was created through stellar nucleosynthesis and scattered across space when massive stars exploded. The timeline of when that happened, how quickly heavy elements spread through the cosmos, how long it took for planets capable of supporting life to form, all of this depends on getting the cosmic timeline right. Moreover, there's something profound about being part of a species that can look out at the universe and ask these fundamental questions. We're matter that has become conscious enough to wonder about its own origins. When we discover that our cosmic timeline might be wrong, we're not just correcting a number, we're refining our understanding of existence itself. The James Webb Space Telescope represents billions of dollars of investment and decades of planning. It's one of humanity's most sophisticated instruments ever created. Positioned at a gravitationally stable point in space called L2, about 1 million miles from Earth, it peers deeper into space and farther back in time than any telescope before it. And now, it's telling us something unexpected. This is science at its finest. Observations challenging theories, mysteries begging for solutions, and the exciting possibility that what we discover might be even stranger and more wonderful than what we imagined. The 6 impossible galaxies aren't just objects in the distant universe. They're messengers from cosmic history, carrying information that could revolutionize our understanding of everything. As we continue this journey through the mysteries of the universe's boundaries and shape, keep these questions in mind. What else might we be wrong about? If the timeline can be off by a factor of 2, what other assumptions need re-examining? And perhaps, most intriguingly, if the universe is nearly twice as old as we thought, what does that mean for the possibility of other civilizations out there, looking up at their own skies and asking the same questions we are? The universe, it seems, still has plenty of secrets to reveal. And thanks to instruments like James Webb, we're only beginning to glimpse just how much we have yet to learn. Part 2. Journey to the Edge of the Universe, the near light-speed travel scenario. Now let's conduct one of the most fascinating thought experiments in all of cosmology. Imagine we've somehow solved all the engineering challenges, built the ultimate spacecraft, and you're one of the lucky few chosen for humanity's most ambitious mission, a journey to find the edge of the universe. Not just a quick hop to Mars or a brief visit to the outer planets. We're talking about a one-way ticket to the absolute limits of existence itself. Your spacecraft isn't bound by conventional rocket fuel or solar sails. For this thought experiment, let's imagine it can accelerate continuously at 10 meters per second squared. Why that specific number? Because it's essentially identical to Earth's gravitational pull. At 9.8 meters per second squared, Earth's gravity keeps us firmly planted on the ground. At 10 meters per second squared, your spacecraft would create artificial gravity that feels exactly like home. You could walk around normally, pour coffee without it floating away, and live comfortably while hurtling toward the cosmos's outer reaches. In the first second of acceleration, your ship moves at 10 meters per second. Not particularly impressive. You could drive faster on a residential street, but remember, this acceleration never stops. Second 2, 20 meters per second. Second 3, 30 meters per second. The numbers keep climbing, and they climb forever. After just 1 hour of continuous acceleration, your spacecraft would be traveling at roughly 36,000 meters per second. That's about 80,000 miles per hour. You'd be moving fast enough to circle the Earth in less than 20 minutes. But you're not circling Earth. You're leaving it behind, and you're just getting started. Here's where the journey begins to showcase the vastness of space. After approximately 35,000 hours of acceleration, which works out to about 4 years, you'd pass the moon's orbit. Think about that. For years of constant acceleration, reaching speeds that would have seemed like pure fantasy to earlier generations, and you've barely left Earth's neighborhood. The moon, that bright disk we see every night, that humans visited in the late 1960s, takes 4 years to pass when you're accelerating at Earth gravity. Keep going. A week into your journey at this relentless acceleration, you'd whistle past Saturn, that magnificent ringed giant floating in the outer solar system. 11 days in, Neptune appears and disappears in your viewport. The farthest major planet from the Sun, that ice giant lurking at the edge of our planetary family. It took Voyager 12 years to reach Neptune. You'd pass it in 11 days. Now, for the sake of this thought experiment, let's ignore some practical concerns. Yes, a spacecraft would need fuel, and the amount required for continuous acceleration would be astronomical, possibly requiring more energy than we could generate with current technology. Yes, space isn't empty. At these speeds, even cosmic dust particles would impact your hull with devastating force, each grain hitting like a bullet. But we're exploring concepts here, not engineering blueprints. We're asking a deeper question. If we could keep accelerating, what would happen? After 15 months of travel, you'd have covered your first light year. 1 light year is the distance light travels in a year. Moving at its cosmic speed limit of about 186,000 miles per second, that's roughly 6 trillion miles. 15 months of constant Earth gravity acceleration gets you there. The nearest star to our Sun, Proxima Centauri, sits about 4.2 light-years away. You'd reach it in about 5 years. At this point, you might think, great. At this rate, we can go anywhere. But the universe has other plans. As your speed increases, you're about to run headfirst into one of the most counterintuitive aspects of reality itself. Einstein's special theory of relativity, special relativity effects. Here's where things get genuinely strange. At first, nothing seems unusual. Your acceleration continues steadily. The crew goes about their routines. Coffee still pours, normally. Gravity still feels like Earth. But as your speed approaches significant fractions of light speed, the fundamental nature of space and time begins to reveal itself. Special relativity tells us something extraordinary. Nothing with mass can reach the speed of light. Not can't because we lack the technology. Can't because it's fundamentally impossible, baked into the structure of reality itself. The speed of light isn't just a really fast speed that happens to be hard to reach. It's a cosmic speed limit, an absolute boundary that no massive object can cross. Think about it this way. In the Large Hadron Collider, scientists accelerate protons to incredible velocities. These subatomic particles reach speeds of about 185,997 miles per second. The speed of light, 186,000 miles per second. The difference, a mere 3 miles per second. That's about the speed of a decent runner. You'd think with all the energy pumped into these particles, adding that final 3 miles per second would be trivial. But it's not. You could pour all the energy in the observable universe into accelerating a single proton, and you still couldn't get it to light speed. You could get it closer, sure. You could add more nines to the decimal, 99.9999999% of light speed, but never 100%. The closer you get, the more energy is required for each tiny increment, approaching infinity as you approach light speed. Without this limit, your spacecraft would have reached light speed in about 45 days of constant acceleration. Simple math. But reality doesn't work that way. Instead, something fascinating happens. After about 45 days, you'd be traveling at roughly 87% of light speed, and that's where the truly weird effects become noticeable. From Earth, watching your spacecraft, assuming they had telescopes powerful enough, observers would see your ship's acceleration appearing to slow down. Time aboard your vessel would seem to pass more slowly. The crew would move as if in slow motion, their clocks ticking at a fraction of normal speed. If you waved at Earth, someone watching through a powerful telescope might see your arm take minutes to complete the gesture. But here's the mind-bending part. From your perspective aboard the ship, nothing would feel different. Your clocks would tick normally. Your coffee would cool at the normal rate. You'd age at the normal pace. Your acceleration would feel constant at 10 meters per second squared, exactly as it always had. To you, time flows normally. It's the rest of the universe that seems to speed up. This isn't symmetrical though. When you look back at Earth, you'd see time there progressing faster and faster. Days would flicker past like seconds. Years would blur. The faster you go, the more pronounced this effect becomes. At 90% of light speed, time slows down by about a factor of 2. Not too dramatic yet. But as you push closer to light speed, the effect intensifies exponentially. The "oh my god" particle example. Want to understand just how extreme this can get? Let's talk about one of the most mysterious and fascinating discoveries in particle physics. On October 15th, 1991, detectors picked up a cosmic particle that scientists immediately nicknamed the "oh my god" particle, not because they were taking the Lord's name in vain, but because when they calculated its energy, their jaws dropped. This single subatomic particle carried as much kinetic energy as a baseball thrown at about 58 miles per hour. Let that sink in. One particle carrying the energy of a baseball. We're talking about something billions of times smaller than a grain of sand, packing a punch you could feel if it hit you. To have that much energy, this particle was moving at an absolutely mind-boggling speed. Get ready for this. 99.9999999999999999999999999999999999999999999999999999999999999999999999999999999 of the speed of light. That's not a typo. That many nines. The particle was so close to light speed that the difference was essentially negligible for practical purposes. Scientists still don't know what accelerated this particle to such incredible speeds. Recent studies have pointed toward a region in the Ursa Major constellation, but that's about all we know. What natural cosmic engine could impart such energy to a single particle? Was it a supermassive black hole? A cosmic string? Some exotic phenomenon we haven't even theorized yet? The question remains open, and frankly, it's a little unsettling not knowing what's out there capable of doing this. But here's the relevant part for our thought experiment. At that speed, time dilation for the particle reached truly staggering proportions. For this particle, time slowed down by a factor of about 300 billion compared to a stationary observer. 300 billion. What does that mean in practice? If this particle traveled from the Andromeda galaxy to Earth, that journey spans about 2.5 million light-years. From our perspective, as stationary observers, that journey would take 2.5 million years, obviously. But from the particle's reference frame, experiencing time at its slowed down rate, the journey would feel like less than 5 minutes. 5 minutes to cross 2.5 million light-years. The entire journey across intergalactic space. A gulf so vast that light itself takes millennia upon millennia to cross, would pass in the time it takes you to brew a cup of coffee. This leads to one of the most profound insights in relativity. For light itself, traveling at exactly light speed, time stops completely. A photon emitted from a distant galaxy billions of years ago doesn't experience any time passing during its journey to your eye. From the photon's perspective, if it could have a perspective, it's emitted and absorbed in the same instant, even if billions of years pass in the external universe, the 8.3 billion light-year threshold. Now, back to your spacecraft, accelerating relentlessly through the cosmos. You've been traveling for subjective decades now. Though centuries or millennia might have passed on Earth due to time dilation, you've passed countless stars, perhaps witnessed galaxies drift by like cosmic clouds, but you're about to cross an invisible boundary, one with profound and terrifying implications. At 8.3 billion light-years from Earth, something changes fundamentally. There's no physical barrier here, no wall or force field. The space looks identical to the space a few million light-years back. But cross this threshold, and you can never go home. Not ever. Not even in principle. Why? It's not because you're moving too fast. It's because of the expansion of space itself. This is crucial to understand. Space isn't static. It's not a fixed stage where galaxies move around like actors. Space itself is expanding, and it's been expanding since the Big Bang. The The farther apart 2 points in space are, the faster they're moving away from each other. Here's an analogy that helps. Imagine a slinky toy, one of those metal springs. Stretch it out. Each coil moves only a small distance from its immediate neighbor, right? Maybe an inch or 2. That's relatively slow, but look at 2 coils at opposite ends of the stretched slinky. During the same time period, they've moved several feet apart. Neither coil moved particularly fast relative to its neighbor, but the cumulative effect across many coils means the ends separate quickly. The universe works the same way. Each unit of space expands slowly, but across billions of light years, those small expansions add up. Distant galaxies can be moving away from us faster than light speed, and there's no violation of physics here. They're not moving through space faster than light. The space between us and them is expanding faster than light. This is what happens when you cross the 8.3 billion light-year threshold. The region of space you're in is moving away from Earth faster than light speed due to cosmic expansion. If you decided right then to turn around, to reverse course and head home, you'd fail. You could fire your engines at maximum thrust. You could accelerate back toward Earth at nearly light speed, and you'd still be moving away from Earth, not toward it. Imagine swimming in a river. You can swim toward shore at 3 miles per hour, but if the current is carrying you away at 5 miles per hour, you're still moving downstream no matter how hard you swim. That's your situation. The current of cosmic expansion is carrying you away faster than you can possibly swim against it. The crew would face an existential horror. They could see Earth's direction. They could point their ship toward home. They could burn every bit of fuel in a desperate attempt to return, and they'd watch as Earth receded farther and farther into the distance, the gap growing wider every second despite their best efforts. There's no coming back. The causal connection with Earth is broken. Whatever happens to you beyond this point can never affect Earth, and whatever happens on Earth can never affect you. You're in separate, disconnected regions of the universe, cut off by the expansion of space itself. Long-term consequences. But let's say you don't turn back. Let's say you accepted before launch that this was a one-way mission, that you'd never see Earth again. You continue accelerating, pushing ever closer to light speed, determined to see what lies at the edge of everything. Time dilation becomes more and more extreme. By the time the ship's internal clocks have logged 200 years of subjective time, 10 generations of crew members born, living, and dying aboard the vessel, an almost incomprehensible amount of time has passed in the external universe. How much? 10 to the power of 41 years. That's A1 followed by 41 zeros. For context, the current age of the universe is about 14 billion years, or roughly 10 to the 10th power years. We're talking about a time span that dwarfs the current age of the universe by an inconceivable margin. What would the universe look like after that much time? Well, according to our current understanding of cosmic expansion driven by dark energy, it would be profoundly different from today's universe. And by different, I mean almost completely empty. Stars have finite lifespans. Our sun will burn for about 10 billion years total. The longest-lived stars, tiny red dwarfs, can burn for trillions of years. But even they eventually run out of fuel. After 10 to the 41st years, essentially every star in the universe would have exhausted its nuclear fuel and died. No more brilliant suns lighting up the cosmos. No more stellar nurseries birthing new stars. Just the cold remnants, white dwarfs, neutron stars, and black holes. But it gets worse. Matter itself isn't eternal. Protons, the building blocks of atomic nuclei, might decay given enough time. The timescale is speculative, maybe 10 to the 34th years, maybe longer, but eternity is patient. Given enough time, even the most stable particles break down. The white dwarfs and neutron stars, those stellar corpses, would gradually disintegrate into radiation and lighter particles. Black holes, those gravitational monsters that swallow everything, aren't immune either. Stephen Hawking discovered that black holes emit radiation due to quantum effects near their event horizons. This Hawking radiation is incredibly feeble for stellar mass black holes. A black hole's a black hole. The mass of our Sun would take 10 to the 67th years to evaporate completely. But again, we're talking about timescales that make that look quick. After 10 to the 41st years, even supermassive black holes, those galactic anchors millions or billions of times the Sun's mass, would have evaporated into nothing. The universe would be left with just photons, neutrinos, and other light particles, spread thinner and thinner as space continues expanding. And here's the truly eerie part. Due to cosmic expansion accelerating over time, your spacecraft would likely be alone in its observable universe. Remember, the farther away something is, the faster it's receding due to expansion. After enough time, everything, every galaxy, every star, every planet, every other spacecraft, if any were launched, would have receded beyond each other's cosmic horizons. Your ship would be traveling through absolute darkness. Looking out the viewport, you wouldn't see stars. You wouldn't see galaxies. You wouldn't see anything but perfect, endless black. The only light would be what the ship generates itself. The only matter would be the ship and its contents. Statistically speaking, within the ship's observable universe, there would likely be no other particles at all. This is the ultimate isolation. Not just cut off from Earth, cut off from everything. The sole island of matter and energy in an ocean of expanding emptiness, with no hope of ever encountering anything else ever again. Would the crew even still be alive at this point? After 200 years of subjective time? Maybe, if they'd achieved some form of life extension, or if the mission was multi-generational. But what would be the point? They set out to find the edge of the universe, and instead found themselves in a universe that had effectively ended around them. Not with a bang, but with an exponential whimper. This thought experiment, as bleak as its conclusion might be, teaches us something profound. The edge of the universe isn't necessarily a place you can travel to. It's not a wall or a boundary waiting to be crossed. Instead, the universe's expansion creates unreachable regions, isolated domains that can never interact with each other no matter how fast you travel. In a sense, the edge of the universe is everywhere and nowhere. It's the cosmic horizon beyond which space is receding too fast for us to ever reach. And that horizon isn't fixed. It's dynamic, expanding in some ways while paradoxically shrinking in others as more and more of the cosmos accelerates beyond our reach. So our first attempt to reach the universe's edge has failed. Not because we lacked the technology or the determination, but because the universe itself refuses to stay still long enough for us to catch up. The cosmos expands, time dilates, and the very act of traveling at extreme speeds puts you out of sync with the universe you're trying to explore. But this raises even more questions. If we can't reach the edge by traveling, what other approaches might work? What do we actually know about the universe's structure and extent? Is there truly an edge at all, or does the cosmos extend infinitely in all directions? And if it does extend infinitely, what does that mean for the nature of reality itself? These questions lead us deeper into the mystery, toward discoveries even stranger than time dilation and cosmic expansion. The universe, we're beginning to realize, doesn't just have secrets. It has secrets within secrets, layers of mystery that challenge everything we think we understand about existence itself. Part 3. Observable universe and reachable limits. Light and observation limitations. Let's start with something that seems simple but has profound implications. We never see anything as it actually is right now. Not your friend across the table, not the moon in the night sky, and certainly not distant galaxies. We always see the past. Always. When you look at someone sitting 3 feet away from you, you're seeing them as they were 3 nanoseconds ago. A nanosecond is 1/1000th of a second. Light takes that long to bounce off them and reach your eyes. The delay is so brief that it's meaningless for practical purposes. Your brain processes visual information slower than that anyway, but the principle remains. You're seeing the past. Look at the moon, that familiar companion hanging in Earth's sky. The light you're seeing left the moon's surface about 1.3 seconds ago. If the moon suddenly vanished, and, let's be clear, it's not going to continue seeing it for another 1.3 seconds before it disappeared from view. During that brief interval, you'd be looking at something that no longer exists. Now extend this principle to the sun. Light takes 8 minutes and 20 seconds to travel from the sun's surface to Earth. When you look at sunrise, you're seeing the sun as it was 8 minutes and 20 seconds in the past. If some cosmic catastrophe vaporized the sun right now, this very second, we wouldn't know for more than 8 minutes. The sky would remain bright, the warmth would continue. Earth would keep orbiting the absent sun for those same 8 minutes and 20 seconds. Why? Because gravity works the same way. This isn't widely appreciated, but it's crucial. Earth doesn't orbit the sun's current position. Earth orbits where the sun was 8 minutes and 20 seconds ago. Gravitational influence propagates at the speed of light, not instantaneously. If the sun vanished, Earth and all the other planets would continue their orbits for 8 more minutes before the gravitational influence ceased and they began drifting off in straight lines into interstellar space. Think about what that means for more distant objects. Betelgeuse, that reddish star in Orion's shoulder, lies about 540 light-years away. When you see Betelgeuse twinkling in the winter sky, you're seeing light that left that star over 5 centuries ago. Back when that light began its journey, Columbus hadn't yet sailed to the Americas. The printing press was just becoming widespread. The Renaissance was in full swing. Betelgeuse is a red supergiant in the final stages of its life. Astronomers know it's going to explode as a supernova relatively soon in cosmic terms. Maybe tomorrow, maybe in 100,000 years. The uncertainty exists partly because we're seeing the star as it was 540 years ago. It could have already exploded. The light from that explosion might be racing toward us right now, and we wouldn't know until it arrives. This time delay becomes even more dramatic when we look at truly distant galaxies. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years away. The light we see from Andromeda left that galaxy 2.5 million years ago, back when early human ancestors were just beginning to use stone tools. But here's something that might surprise you. Andromeda is actually about 900 light-years closer than it appears. How is that possible? Because Andromeda is heading straight toward us at approximately 250 miles per second. In the 2.5 million years it took for the light to reach us, Andromeda has covered about 900 light-years of the distance. We're seeing where it was, not where it is now. Don't worry about an imminent collision though. Despite that impressive closing speed, Andromeda won't reach us for another 4 billion years or so. When it does, the resulting merger will reshape both galaxies, possibly creating a new elliptical galaxy that astronomers have already nicknamed Milky Way. But that's a story for another time. The key point here is this. When we look into deep space, we're not just looking far away, we're looking back in time. The farther we look, the further back we see. And that brings us to a crucial concept for understanding the universe's boundaries: the 46 billion light-year paradox. Here's a question that confuses a lot of people, and understandably so. If the universe is about 14 billion years old, how can we see objects that are 46 billion light-years away? Light's been traveling since the Big Bang, right? So shouldn't the farthest we can see be 14 billion light-years? The answer is no. And understanding why requires grasping one of the most important concepts in modern cosmology: the expansion of space itself. Imagine light leaving a distant galaxy shortly after the Big Bang. That light begins traveling toward the point in space where Earth will eventually form. But while that light is traveling, space itself is expanding. Not the galaxies moving through space, but space itself stretching like rubber. Think of it like this. You're walking forward on a treadmill that's also moving backward. Your walking speed stays constant, but your progress depends on the treadmill's speed too. If the treadmill moves backward slower than you walk forward, you make progress. If it moves backward faster than you walk, you go backward despite walking forward. Light works similarly. Photons travel through space at light speed, always. But if space itself is expanding, the photons' progress toward us depends on both their travel speed and the expansion rate of the space they're traversing. In the early universe, the expansion rate was lower. Light could make steady progress toward our location. But as the universe aged, dark energy began dominating cosmic dynamics, causing expansion to accelerate. The space between distant objects began stretching faster and faster. So light that's been traveling for 14 billion years hasn't covered just 14 billion light. The space it crossed has been stretching the entire time, meaning the source of that light is now much farther away than 14 billion light-years. Current calculations put it at about 46 billion light-years in any direction. That means our observable universe has a diameter of roughly 92 billion light-years. That's the cosmic horizon, the boundary beyond which light hasn't had time to reach us yet since the Big Bang, accounting for expansion. But here's the crucial thing to understand. Observable doesn't mean reachable. There's a fundamental difference between what we can see and what we could theoretically travel to, even at light speed. And that difference creates some of the most counterintuitive and frankly disturbing implications in all of cosmology. Observable universe layers. Let's break down the observable universe into distinct zones based on what we can see and what we can reach. Think of these as concentric shells around Earth, each with different properties and possibilities. The first zone extends from Earth out to about 15 billion light-years. Within this sphere, we find approximately 66 billion galaxies. These galaxies are, at least in principle, reachable. If we could somehow travel at or near light speed, we could eventually get there. The crew from our thought experiment in the previous section, accelerating continuously at Earth gravity, could reach any destination in this zone given enough time. When we observe galaxies in this zone, we see them as they were in the past, of course. A galaxy 10 billion light-years away appears as it was 10 billion years ago. But the light those galaxies are emitting right now will eventually reach us in the future, billions of years from now. Humans, or their descendants, or whatever intelligent beings inherit Earth, will be able to see those galaxies as they are today. The information is just delayed, not lost. This is the accessible universe. Not accessible with current technology, obviously. We can barely send probes to the outer planets. But accessible in principle, given sufficient technological advancement and time. Now move outward, to the zone spanning from 15 billion to 46 billion light-years. This region contains approximately 2 trillion galaxies. 2 trillions? That's a staggering number. So large it's hard to conceptualize. For comparison, the Milky Way contains maybe 400 billion stars. We're talking about 2 trillion entire galaxies, each potentially containing hundreds of billions of stars. Here's where things get strange. We can see these galaxies, but they're forever beyond our reach. Even if you could travel at exactly light speed, you could never get there. The expansion of space between us and them is accelerating faster than light can cross it. These galaxies are receding from us at superluminal speeds, but we can still observe them, right? We see their light, arriving after journeys spanning billions of years. The catch is this: we'll always see them as they were in the distant past. We'll never see these galaxies as they are today. For us, they're frozen in time, ancient photographs never to be updated. Think about what that means. There's a galaxy out there, let's call it Galaxy X, sitting 25 billion light-years away. We can see it through our most powerful telescopes. We can study its structure, measure its composition, watch it as it was 25 billion years ago. But the light that galaxy is emitting right now, today, this very moment, will never reach Earth, ever. It's not that we need better telescopes or more time. It's that the expansion of space makes it fundamentally impossible for that light to ever complete the journey. The space between us and Galaxy X is stretching faster than light can cross it. We're seeing a farewell photograph, an image that will slowly fade and redshift into nothingness over the eons. Astronomers sometimes call this the cosmic horizon recession. Galaxies we can currently see will, over billions of years, fade from view as they cross over our cosmic horizon. Their light will stretch to longer and longer wavelengths. From visible light to infrared to radio waves to wavelengths so long they become undetectable. And then they'll be gone from our sky forever. Move farther out still, to the zone from 46 billion to 61 billion light-years. These galaxies we cannot see yet. The light they emitted shortly after the Big Bang hasn't reached us. It's still in transit, crossing the vast distances of expanding space. But someday, if humanity or its successors are still around, we'll see those galaxies for the first time. Future astronomers, perhaps a billion years from now, will point their telescopes at a region of sky that appears empty to us and discover new galaxies appearing. Light arriving from the deep past of the universe. It'll be like developing a photograph that's been exposing for eons. New details gradually emerging from the darkness. But this is crucial. These galaxies are also unreachable. By the time their light arrives, they'll be so far away, receding so fast, that no amount of technology could ever close the distance. We'll get to see them once, in their ancient form, and then watch them slowly fade like all the others. Finally, beyond 61 billion light-years lies the truly unknown. Galaxies at these distances cannot be seen by us or anyone else, now or ever in the future. Their light will never reach our cosmic horizon. We have no idea what's happening in those regions. For all practical purposes, they don't exist in our universe, even though they presumably contain countless galaxies, stars, and possibly even other civilizations asking the same questions we are. The GNZ11 galaxy example. Let me make this concrete with a real example. Astronomers have identified a galaxy designated GNZ11. Don't worry about the technical name. What matters is that GNZ11 is one of the most distant galaxies ever observed. The light we're seeing from it was emitted about 13.4 billion years ago, when the universe was only about 400 million years old. That's incredibly young in cosmic terms, less than 3% of the universe's current age, due to the expansion of space during the light's journey. GNZ11 is now located about 32 billion light-years from Earth. That places it in the second zone we discussed, beyond the 15 billion light-year threshold. What we see when we look at GNZ11 is ancient light, a snapshot from the universe's infancy. But here's the heartbreaking part. GNZ11 is currently receding from us at about 687,000 kilometers per second. For context, light speed is about 300,000 kilometers per second. GNZ11 is moving away at more than twice the speed of light due to cosmic expansion. This means the image we're seeing is a farewell photograph. The light GNZ11 is emitting right now will never reach Earth. That galaxy, as it exists today, is forever beyond our knowledge. We can study its past, learn about its early structure and composition, but we'll never see it mature. We'll never know what became of it. As billions of years pass, the image we see will fade, redshift, and eventually vanish from our instruments entirely. It's like finding an old photograph of someone you'll never meet. Someone who lived in a place you can never visit, frozen in a moment that's long past. GNZ11 exists, presumably. It might still be there, evolved and changed over billions of years. But for us, it's lost, separated not by simple distance, but by the fundamental structure of an expanding universe. This example illustrates something profound. We live in a universe that's not just large, but structured in a way that creates permanent, unbridgeable gaps in our knowledge. There are things we can never know, places we can never reach, not because of technological limitations, but because of the basic laws governing cosmic expansion, disappearance statistics. Now, let's talk about some numbers that should genuinely disturb you. Over the history of the universe, stretching back to the Big Bang, there have been countless galaxies within our cosmic horizon at various times. Not all of them remain observable. In fact, most of them don't. Here's the math. Astronomers estimate that we'll eventually be able to observe, over all time past and future, approximately 4,700 billion galaxies. That's the total number that will ever appear within our cosmic horizon at any point in cosmic history. Of those 4,700 billion galaxies, about 4,634 billion have already crossed beyond our reachable threshold. That's roughly 98.6%. We're seeing their ancient light, yes. We can study them, yes. But the light they're emitting right now will never reach us. They're lost, slipped beyond the cosmic horizon, forever out of reach. That leaves about 66 billion galaxies still within our reachable zone. 66 billion sounds like a lot, and in absolute terms, it is. But it's only about 1.4% of the total. And this number is shrinking. How fast? Let's assume each of these 66 billion galaxies contains, on average, about the same number of stars as the Milky Way. That's approximately 400 billion stars per galaxy. The math works out to about 60,000 stars disappearing beyond our cosmic horizon every single second. Think about that. In the time it's taken you to listen to this section, several million stars have crossed the threshold into permanent unreachability. Since you started watching this documentary, tens of millions of stars have vanished from the accessible universe. They haven't been destroyed. They haven't ceased to exist. They're just irrelevant now, in a very real sense. Whatever happens to them cannot affect us. Whatever we do cannot affect them. The causal connection has been severed by the expansion of space, and this process is accelerating. Dark energy, that mysterious force driving cosmic expansion, grows stronger as the universe contains more empty space. As galaxies cross the horizon and fade from view, more empty space remains. More empty space means stronger dark energy. Stronger dark energy means faster expansion. Faster expansion means more galaxies crossing the horizon. It's a feedback loop, and we're on the losing end of it. The universe we can interact with is shrinking, even as the universe as a whole expands. Future astronomers, assuming civilization lasts that long, will look out at an increasingly empty cosmos. Billions of years from now, when the sun has swelled into a red giant and potentially consumed Earth, the night sky for any surviving civilizations will look vastly different. Many of the galaxies we see today will have faded beyond detection. The universe will appear lonelier, darker, emptier. Trillions of years from now, when even long-lived stars have exhausted their fuel, the last civilizations might look up and see essentially nothing beyond their own galaxy or local cluster. The rich tapestry of galaxies visible to us would be gone, vanished beyond a horizon that can never be crossed. Eventually, given enough time, each galaxy becomes an isolated island in an expanding void. The Milky Way, or whatever it becomes after merging with Andromeda, will be alone. No other galaxies visible, no light arriving from distant cosmic shores, just darkness, expanding emptiness, and the slow death of the last stars. This is the ultimate fate predicted by our current models. Not a big crunch where the universe collapses back in on itself. Not a big rip where expansion accelerates so violently that it tears apart atoms themselves, but a slow, cold, lonely dissolution. Galaxies drifting apart, stars burning out, black holes evaporating, until nothing remains but thin radiation in an ever-expanding void. It's a bleak vision, and it stems directly from the properties of dark energy and cosmic expansion. The universe isn't just large, it's structured in a way that guarantees increasing isolation, separation, and ultimately, darkness. Yet we're living in what might be considered a golden age of cosmology. We can still see much of the cosmic web, the large-scale structure of the universe. We can study galaxies at various distances and stages of evolution. We can piece together the history of cosmic development. Future civilizations might not have that luxury. They might look out at an empty sky and wonder if they're alone, not knowing that billions of galaxies exist beyond their cosmic horizon, forever out of reach. This brings us to perhaps the most unsettling implication. We're losing information. Every galaxy that crosses the cosmic horizon takes with it unique information about its structure, evolution, and contents. That information becomes fundamentally inaccessible. It's not hidden or difficult to access. It's gone, in the sense that no future observation could ever recover it. In information theory, this is troubling. We like to think that information is conserved, that data isn't truly destroyed. But cosmic expansion violates this principle on the largest scales. Information is being lost, not to black holes where it might arguably be preserved in some form, but to cosmic horizons where it's simply removed from any possible interaction with our region of space-time. What does this mean for the universe as a whole? If different regions are permanently isolated, unable to influence each other, are they still part of the same universe? Or have they effectively become separate universes, distinct realities with no causal connection? These aren't just philosophical questions, they get at the heart of what we mean by the universe and whether that concept even makes sense in a cosmos dominated by accelerating expansion. If the universe is everything that exists, but large portions of what exists can never interact with us, are those portions meaningfully part of our universe? The observable universe, we're learning, is just a tiny fraction of what might exist. And even that fraction is shrinking, galaxies slipping away into darkness, information lost to expansion. We're seeing the universe during a brief window when much of it remains visible. Our distant descendants might not be so fortunate. This realization adds urgency to our current cosmological studies. We need to observe and catalogue as much as we can while we still can. Future generations won't have access to the full cosmic picture we can see today. In a very real sense, we're the custodians of information about the universe that will eventually be lost forever. So when you look up at the night sky and see those distant galaxies shining in deep space images, remember, you're seeing farewell photographs. Images frozen in the ancient past, from places that are slipping away from us at speeds we can never match. The universe is vast beyond comprehension, but it's also structured in a way that ensures most of it will forever remain beyond our reach. Not just practically, but fundamentally, and that raises even deeper questions about the nature of the cosmos itself. If most of the universe is unreachable and unknowable, what does that say about reality? What lies beyond our cosmic horizon? And is there any sense in which the universe has an edge, or does it extend infinitely in all directions, filled with galaxies and structures we'll never see? To answer these questions, we need to dig deeper into the geometry and topology of space itself, exploring concepts that challenge our everyday intuitions about the nature of reality. Part 4. The shape and topology of the universe. The flat universe paradox. Here's something that sounds absurd at first. The universe might be flat, not Earth we've established that's roughly spherical, but the universe itself, all three dimensions of space, might be geometrically flat. What does that even mean? Let's start with a story about one of history's greatest mathematical minds. Carl Friedrich Gauss, working in the early 19th century, began suspecting something strange about the geometry of space. He knew that on a perfectly flat surface, the angles of any triangle always add up to exactly 180 degrees. Always. It's one of those mathematical truths that seems unbreakable. But Gauss wondered, what if we don't live on a flat surface? Imagine you're a two-dimensional being living on the surface of a sphere, like Earth. If you draw a small triangle on the ground and measure its angles with basic tools, you'd get 180 degrees. But if you drew an enormous triangle, one spanning thousands of miles, something different would happen. The curvature of Earth's surface would become noticeable, and the sum of the angles would be greater than 180 degrees. Gauss hypothesized that our three-dimensional space might have curvature too, just like the two-dimensional surface of Earth curves through a third dimension. If so, measuring the angles of a sufficiently large triangle should reveal that curvature. The sum would deviate from 180 degrees in detectable ways. So Gauss did something remarkable. He secretly used surveying equipment to measure a triangle formed by 3 mountain peaks in Germany. Why secretly? Because if his colleagues found out that this respected mathematician was seriously testing whether triangles might not add up to 180 degrees, they'd think he'd lost his mind. The results? The angles did show a slight deviation from 180 degrees, but the deviation fell within the margin of measurement error. Gauss couldn't determine whether space was truly curved, or if his instruments just weren't precise enough. Decades later, Einstein's general theory of relativity proved that space does curve near massive objects. GPS satellites have to account for this curvature. Near Earth, the angles of a sufficiently large triangle would indeed deviate from 180 degrees by about 0.2 degrees. Not much, but measurable with modern instruments. This confirmed that space curves locally around massive objects. But what about space as a whole? Does the universe have an overall curvature? This question has profound implications for whether the universe is finite or infinite, whether it has boundaries or loops back on itself. Modern cosmologists have attempted to answer this by measuring the geometry of space on the largest scales possible. They've examined the cosmic microwave background radiation, that faint glow left over from the Big Bang. They've studied how light from distant galaxies bends and travels. They've looked for telltale signs of curvature in the large-scale structure of the cosmos. The results are striking. Within our ability to measure, the universe appears flat, not approximately flat. Flat to within 99.75% accuracy. The angles of cosmic triangles add up to 180 degrees as far as we can tell. But here's the crucial caveat. That doesn't mean the universe is infinite. It just means that if it's curved, the curvature is so slight that we can't detect it yet. Think of it like standing on Earth. The ground beneath your feet looks flat, but you know Earth is spherical. You just can't see the curvature from your limited vantage point. If the universe is curved but appears flat to us, it must be enormous. Calculations suggest it would need to be at least 400 times larger than the observable universe. We're talking about a diameter of at least 37 trillion light-years. That's so large that any curvature becomes undetectable with current technology. 18 possible universe forms. Now we get into territory that's genuinely mind-bending. Mathematicians and cosmologists have worked out that there are exactly 18 possible topologies for a three-dimensional universe. 18 different shapes the cosmos could take, each with radically different implications for what the universe is like on the largest scales. These topologies fall into two categories: orientable and non-orientable. That terminology sounds technical, but the concept is actually fascinating. Let me explain with an example that'll make your brain hurt in the best possible way. Consider a Mobius strip. Take a strip of paper, give it a half twist, and connect the ends. You've created a non-orientable surface, also called one-sided. Here's the weird part. If you draw a small arrow on the strip pointing in one direction, then slide that arrow around the strip's length, when it returns to the starting point, the arrow will be pointing the opposite direction. You flipped it without ever lifting it off the surface. Now imagine you're a two-dimensional being living on this Mobius strip universe. You decide to take a trip around your cosmos. You start with your heart on the left side of your body, and off you go. When you complete the circuit and return home, something strange has happened. Your heart is now on the right side, not because it moved, but because you traveled along a path that reversed your orientation. You've become your own mirror image. If our three-dimensional universe were non-orientable in certain ways, similar things could happen. You could launch a spacecraft on a journey through space, and when it returned, everything aboard would be reversed. Left and right would swap. Clockwise would become counterclockwise. Particles would become their mirror image versions, and matter might even transform into antimatter. Sounds like science fiction. It is, probably, Cosmologists generally believe we don't live in a non-orientable universe. The reason is simple. If we did, there should be boundary zones scattered throughout space where normal matter meets its mirror-reversed version. At these boundaries, matter and antimatter would interact and annihilate, releasing tremendous amounts of energy. We'd see powerful radiation sources dotted across the sky. We don't see that. The universe appears orientable, at least within the regions we can observe. Of course, if the universe is vastly larger than what we can see, those boundaries might exist beyond our cosmic horizon. We'd never know. The orientable topologies include some fascinating possibilities. The simplest is an infinite flat space extending forever in all directions. But there are also closed orientable spaces, like a three-dimensional version of a sphere's surface or a torus. These would be finite in volume but have no edges. Similar to how Earth's surface is finite in area, but you can walk forever without hitting a boundary. Closedness and the infinity paradox. Here's where the concept of cosmic topology gets really interesting. A universe can be finite without having edges. This sounds contradictory until you think about it carefully. Consider Earth's surface again. It's a finite, two-dimensional surface with a specific, measurable area, but there are no edges. You can walk in any direction forever, and you'll never reach a boundary. Eventually, you'll circle back to where you started, but you won't encounter any walls or limits. The universe could work the same way in 3 dimensions. Imagine all of space is somehow curved back on itself, forming a closed 3-dimensional surface embedded in a 4-dimensional space we can't perceive directly. In such a universe, you could fly your spacecraft in a straight line forever and eventually return to your starting point, having circumnavigated the entire cosmos. This wouldn't violate the flatness measurements we discussed earlier. Just as a cylinder has a flat surface, despite being topologically closed in one direction, the universe could be geometrically flat while still being topologically closed. You could draw triangles whose angles sum to 180 degrees, yet still eventually loop back through space. Different closed topologies create different patterns. In a spherical universe, if you looked far enough in any direction, you'd eventually see the back of your own head. Assuming you could see far enough and light had time to complete the circuit. In a toroidal universe, space would wrap around in multiple directions, creating a more complex pattern of repeating images. Could we detect this? Potentially, if the universe is closed and small enough relative to our observable region, we might see repeating patterns in the distribution of galaxies. We might identify the same galaxy appearing in multiple locations in the sky, its light having reached us via different paths through wrapped space. So far, searches for such patterns have come up empty, suggesting that if the universe is closed, it's too large for us to detect the repetition. Curvature measurements. Scientists have thrown enormous resources at measuring the universe's curvature. The most precise measurements come from examining the cosmic microwave background, that faint radiation filling all of space, left over from when the universe was only 380,000 years old. The CMB shows tiny temperature fluctuations, hot and cold spots varying by about 1 part in 100,000. These fluctuations are like fossils of the early universe, preserving information about conditions shortly after the Big Bang. The size and distribution of these spots depends on the geometry of space. If space were positively curved like a sphere's surface, the spots would appear larger than expected. If space were negatively curved like a saddle, the spots would appear smaller. If space is flat, the spots have a specific characteristic size. Measurements from satellites, like WMAP and Planck, have nailed down this geometry with impressive precision. The answer, flat, to within a tiny margin of error. The universe's curvature, if it exists at all, must be incredibly slight. This flatness creates the infinity problem. If the universe is truly flat and extends indefinitely, it's infinite. And as we discussed in our previous section, an infinite universe leads to some genuinely disturbing philosophical implications. Every possible configuration of matter would occur infinitely many times. There would be infinite copies of you, infinite Earths, infinite everything. Many scientists find this uncomfortable. The alternative is that the universe is closed, finite in volume, but so large that its curvature remains undetectable. We're living inside a cosmic structure so vast that it appears flat from our limited perspective. Just as Earth's surface appears flat when you're standing in a field, which is true, we honestly don't know. Current observations can't distinguish between a truly flat, infinite universe and a very slightly curved, very large, closed universe. Both possibilities remain on the table, and both have profound implications for the nature of reality itself. What we can say is this: if the universe is closed, it's enormous. At minimum, based on our measurements, it must be 400 times the diameter of the observable universe. That's a mind-boggling scale. So large that entire observable universe-sized regions could be scattered throughout it like grains of sand on a beach. The shape of the universe isn't just an abstract mathematical curiosity. It determines whether the cosmos is finite or infinite, whether it has an edge or loops back on itself, whether reality is ultimately bounded or boundless. These questions touch on the deepest mysteries of existence. And remarkably, we're using actual observations and measurements to constrain the answers. As we move toward our final section, we'll confront perhaps the strangest possibility of all, that the universe might be infinite, and what that truly means for the nature of reality and our place within it. The implications are more bizarre than most people imagine, leading to conclusions that challenge our understanding of uniqueness, probability, and existence itself. Part 5: Infinite Universe and the Fourth Dimension. The fourth dimension as the true edge. We've journeyed through cosmic expansion, observable horizons, and geometric possibilities. We've watched galaxies slip beyond reach and contemplated universes that loop back on themselves. But there's one boundary we haven't fully explored, one that's been hiding in plain sight all along: the fourth spatial dimension. To understand this, let's imagine a two-dimensional universe, a flat plane stretching infinitely in two directions. Picture tiny two-dimensional beings living there, creatures with length and width but no thickness. Their entire existence plays out on this flat surface. They can move forward, backward, left, and right, but the concept of up and down simply doesn't exist in their reality. Now imagine we three-dimensional beings are observing this flat universe from our higher dimensional perspective. Something remarkable happens. We can see everything simultaneously. Every molecule of their two-dimensional world is spread out before us like a map. There are no hidden interiors, no unexplored depths. If their world contains two-dimensional atoms, we see every single one at once, laid bare in perfect clarity. Where is the edge of their universe from our perspective? It's not at some distant boundary they could travel to. The edge is the third dimension itself, pressing against their flat reality from a direction they cannot perceive, cannot point to, and cannot comprehend. It's everywhere and nowhere, surrounding every point of their existence. Now make the leap. We live in three spatial dimensions. We move through length, width, and depth with ease. But what if there's a fourth spatial dimension, perpendicular to all three of ours in a way we can't visualize? What if our entire three-dimensional universe is embedded in a higher dimensional space? If such a dimension exists, then just as we could see every atom of the two-dimensional universe, a four-dimensional being could see every atom of ours, all at once, nothing hidden. The interior of your body, the core of planets, the heart of stars, all would be visible simultaneously from that higher perspective. And the edge of our universe, it wouldn't be some distant wall 46 billion light-years away. It would be right here, right now, pressing against every point in space from a direction we cannot perceive. The fourth dimension would surround us completely, saturating every cubic centimeter of reality, yet remaining forever beyond our direct interaction. This is perhaps the most profound answer to our original question about the universe's edge. The boundary isn't out there in the distance. It's here, intimately close, woven into the fabric of every moment. We're literally swimming in it, moving through it with every breath, yet unable to perceive it because our senses and our consciousness are locked into three dimensions. A warm farewell. We've explored some of the deepest mysteries the cosmos has to offer. We've watched the James Webb Telescope challenge our understanding of cosmic history. We've taken imaginary journeys at light speed and witnessed the heartbreak of cosmic expansion pulling galaxies beyond reach. We've contemplated shapes of space that defy everyday intuition and touched on the possibility of infinite realities. These aren't just abstract concepts, they're descriptions of the actual universe we inhabit, the cosmos that birthed the atoms in our bodies and will exist long after we're gone. Every question we've explored tonight connects to something fundamental about existence itself. As you finish watching this, perhaps you'll step outside and look up at the night sky with fresh eyes. Those stars you see, that darkness between them, all of it is part of this grand cosmic story. You're standing on a small world orbiting an average star in an ordinary galaxy, yet you're capable of understanding things about the universe that took billions of years to arrange the matter necessary for consciousness to emerge and ask these questions. That's remarkable. You're remarkable for caring about these mysteries, for wondering what lies beyond, for contemplating the shape and fate of everything. The universe may be expanding, galaxies may be slipping away into darkness, but right now, in this moment, you're here. You exist in a time when much of the cosmos remains visible, when we can still study distant galaxies and ancient light, when the night sky tells stories spanning billions of years. Rest well tonight, knowing you've touched something infinite. The questions we've explored together will remain long after we're gone, waiting for future minds to puzzle over them. But for now, they're yours to contemplate as you drift off to sleep. The universe is vast, mysterious, and perhaps ultimately unknowable in its entirety, but it's also your home. And that makes you a part of something extraordinary. Sweet dreams, fellow cosmic explorer. May your thoughts be as vast as the universe we've journeyed through together.